In this lecture, we will study common source amplifier, but this time we will talk about how the voltage gain varies for low frequency. And you can recall that in the last lecture, we discussed the voltage gain of common source amplifier for high frequency. So this is the circuit that we analyzed. In fact, this was the second circuit which we analyzed. In the first version, we had excluded this RS, which we included later on. So for this circuit, we found that magnitude of the voltage gain is going to vary like this, as shown here. It will be flat for the smaller values, and then it will start reducing with the slope of minus 20 dB per decade, then minus 40 dB, and then finally minus 20 dB. So actually all these, especially the behavior in this region, will be decided by the which of these poles WP2 or the 0 WZ is smaller. So, but nevertheless, response is in general going to be like this. And if someone performs the actual experiment, what they will get is behavior like this one, this green color. So here keep in mind that although we have extended this lower side curve up to here, you can say going up to 0 omega, but this one is valid only uh, for sufficiently high frequency. So actual portion of the curve that we will be interested in, or which will be more accurate, is this much. And this is the low frequency region for which we are going to carry out the analysis today, right? But this is going to be the maximum value that you will get, and the maximum value here is equal to GMRD. And we are familiar with this term, and this is actually the voltage gain for low frequency. This is what we arrived at when we started the discussion of amplifier. But keep in mind, all these result that we have obtained is for this circuit, right, where we haven't included the biasing resistors. These R1 and R2, they have been excluded, assuming that they are very large. But if you include them, this result, the low frequency value, will definitely get modified, and there might be some change in the numerical value of these poles and zeros, and maybe their relative relation also. But in general, there will be decay in the gain starting from certain value. This could be pole omega p1 or omega p2, right? Very rarely we'll find that there will be this kind of response, that from here you will start getting increment in gain. That rarely happens, and we can justify also that why we will never get this increasing kind of behavior, at least in the beginning, and why there will always be this decreasing, on the whole decreasing type of gain. So for that, we can see the small signal model here. So this is the small signal model of the circuit that I showed just now, and I claim that there will always be decay in the voltage gain as the frequency increases. So keep in mind that the most important factor in deciding this voltage gain is this voltage VGS, voltage across this capacitor, right? And this voltage is going to be decided by the of course current and the impedance offered by this. So impedance offered by this CGS is going to be 1 by j omega CGS. So as frequency increases, this impedance is going to decrease, and this will imply that VGS decreases with the frequency. When VGS decreases, this dependent current source IG is also going to decrease. So in general, there will be decrement in this output voltage, because this output voltage is nothing but being developed because of the IG that is flowing through this plus ID that is flowing through RD. And since IG decreases, so this VO is also going to decrease. And this will then finally imply that AV decreases. So you see that main reason why voltage gain in general will reduce when the frequency increases is because this impedance offered by CGS capacitor is going to decrease, right? So from here you can be now sure that there will be never this kind of response. It will always be decreasing kind of response. This is the kind of actual response that you will see. It will always decrease. Right. So now we want to see that how the circuit will behave for the low frequency. So now let us see the exact circuit. Uh, so for this, we will have to start from the complete circuit, and the complete circuit is this one with all the biasing network. Yeah. So last time when we discussed the high frequency response, we considered only this much part, right? And we excluded R1 and R2. They could have also been included, but it would have only complicated the analysis. So that is why we excluded. But we will see that this time we will have to include it. We cannot exclude them. So for low frequency response, what we will have to do is, of course, exclude all the MOS capacitors. That means capacitors which are there inside MOS. And reason is that you can see that they will now be offering very high impedance because frequency is very low. The CGS and all other capacitor, they are already very low. And I have mentioned here CGS because CGS is largest out of all the internal 4 capacitors that we talked about. So here you can see that since the frequency is very small, CGS is very small, so this impedance is going to be very small, and that is why there will be hardly any current between, say, gate and source, or gate and drain, or source and bulk, which in fact is anyway not going to be there between drain and bulk. So those capacitors, they will be behaving like open circuit, extremely high impedance, and that is why for the low frequency we do not include them in the small signal model. So we are now going to draw the small signal model by excluding these MOS capacitors. So then draw the, and this time you will have to include this external capacitors, because as pointed out, these will be typically of order of microfarad, so their impedance will be non-negligible. they will neither act like a short circuit nor like an open circuit, so they have to be there. So now we draw the small signal model of MOS. So here we have RD on the drain side, and this is our output. Source is grounded, and on the input side we have RS, then capacitor CI, and then two resistors R1 and R2. So R2 is grounded here, R1 will also be AC grounded at the other end. So R1 and R2, they will be basically in parallel. So there is one resistor, R1 parallel R2. And then here we have our input, right? So here you can see that source and other end of the bias resistor, they are grounded. So we can combine them and represent in this way. So here the important voltage is VGS, which actually becomes the voltage across this parallel R1 and R2 bias resistors. Right. So now we have to find out VO. So VO is minus RD GMVGS, which is minus RD GMVG. Source is grounded, right? So we need to find out this voltage VG, right? So this voltage VG is voltage across this parallel resistor, right? So we can write the voltage across it as R1 parallel R2 divided by R1 parallel R2 plus RS plus XCI into VI. So we have three impedances here in path, RS, CI and R parallel, right? So we can then write VO as minus RD GM R1 parallel R2 divided by R1 parallel R2 plus RS plus XCI into VI, where XCI is 1 by J omega Ci, or in form of S it can be also represented like this. Right, so now we can rewrite this in form of, in terms of S, because the voltage gain AV for low frequency is VO by VI equal to minus RD GM R1 parallel R2 plus RS plus this can be written as SCI. So we can simplify this, and this will give RD GM R1 parallel R2 SCI divided by R1 parallel R2 plus RS CIS plus 1. So this is the low frequency voltage gain of common source amplifier. Now we'd like to do the Bode plot to see that how the voltage gain is going to vary with frequency. So we will have to write it in standard form. This you can see that it is already in the factorized form. The numerator has 1 0 at the origin, right? And the denominator has one pole, not at origin, at some other location. Both are already of first order form, so we just need to write them in standard form. So here we can write S divided by 1 by R1 parallel R2 plus RS into Ci plus 1, and in numerator we have minus GMRD R1 parallel R2 Ci and S. Yes. So here this implies that we have one constant term GMRD R1 parallel R2 Ci, 10 at origin, designated by presence of S in the numerator, and we have a pole at omega p is equal to 1 by R1 parallel R2 plus RS into Ci. So here I would like to point out one thing which we will be using later on, that you see that this pole is always of this form 1 by R into C. Okay, so this fact you keep in mind. We will utilize this fact later on in future classes. Okay, so this is the transfer function, and now we would like to do the Bode plot. So there will be three curves, and the overall curve is going to be the sum of all these three curves. So first we have this constant term. So we have constant K is equal to GMRD R1 parallel R2 into Ci. So there will be a horizontal line which will be 20 log K, right? And then we have 0 at origin, so there will be a straight line passing from origin. That means omega is equal to 1, and it will of course have slope of plus 20 dB per decade. And then we have a pole here. Let us say it is located here. So you will have the third curve like this, which will have a slope of minus 20 dB per decade. So these are the three curves, and overall response is going to be sum of this one. So here you can see that for the lower frequency, the third term pole has no effect. So this constant term and the 0 term, they will dominate. So the 0 crossing point of 0 will get shifted here. So we are going to get a curve like this. So it is this curve which shifts here to this constant term, and this will continue till omega p. At the rate of plus 20 dB for every 10-fold increment in the frequency. So after this, the plus 20 dB slope of this 0 will get cancelled out by minus 20 dB slope. That means both this will increase the curve by plus 20 dB, pole will decrease the curve by 20 dB minus 20 dB. So net increment is going to be 0. So this will become horizontal flat like this. right? So we are going to get this red curve as the Bode plot of the low frequency voltage gain, this AVL. This is the magnitude of AVL, right? And actual response, if you carry out experiment, is of course going to be like this here. So you see that the two straight lines, they are going to be tangent, one at very low frequency 0, other is going to be tangent at infinity. And there will be maximum mismatch between Bode plot and the actual curve here at the omega p. And these are also called corner frequency because you can see that curve takes turn. Right. So here one question will arise is that what is the value of this horizontal line? This value, what is this numerical value of this level? So one quick way of finding out this is that here you can see that this line is basically tangent to the actual one at infinity. That means when omega is infinite or s is infinite, that time the value of AVL is going to be this value that we are trying to find out. So we can go to the expression for AVL and then try to find out its value at infinity. So here, if you find out AVL for S or omega going to infinity, what you are going to get is that value that we are looking for, right here. So if we take a limit for infinity, so we will divide it by S and then take the limit. So here you can see that when you take the limit, it is only this term which will become 0. Rest all will survive. And when rest all survive, C and C will get cancelled out. And what will be left is this factor, which is GMRD R1 parallel R2 divided by R1 parallel R2 plus RS, right? So this horizontal line is basically AVL magnitude at infinity, and at infinity its value just now we saw magnitude is GMRD R1 parallel R2 divided by R1 parallel R2 plus RS. So this is going to be the value at infinity, or this value. So now we have a low frequency response of common source amplifier, and we have high frequency response. So one can ask that what will be the combined response. That means if we try to plot an approximate curve from very low frequency to very high frequency. So here we have now two types of plots. AVL, which we saw was like this at omega p, and then AVH, high frequency response, which we saw was like this. So our objective is now to combine them and try to see if we can have a single plot giving the complete response. And here the value that we got was GMRD R1 parallel R2 divided by R1 parallel R2 plus RS. This value which seems to extend up to infinity. But in this case, value that we got was GMRD, which goes up to low frequency. That means omega is equal to 0. So both have a flat response in the region, because when you combine, this region will get combined together, right? Because here, although we are showing this curve for low frequency, but once again, as I pointed out, this portion falls in the region of low frequency. Similarly, this portion falls in the region of high frequency. So actually this much portion should be the response coming from here, and this portion should be response coming from AVH. Let me say that these are the magnitude. Y-axis is always magnitude, even if I don't show it, right? But the problem here is you can see that their values, they are not same. In one case we are getting this value, other case we are getting this value. So they possibly cannot be combined, and we cannot get this kind of response which appears from the combination of these two. Suppose we add these two, so we should get this. So question will arise, what is this value, right? Because in both the cases we have different number. Here we have something else, here we have something else. So this is happening because actually we did not consider exactly same circuit for both the responses. For finding out high frequency response, we neglected R1 and R2. So these factors were neglected for finding out high frequency response, but they were included in the low frequency response analysis. So we will now have to actually include this R1 and R2 also to find out a high frequency gain. Then we can find out what is the exact value here, right? So if we try to include R1 and R2 also in the high frequency response, the exact analysis will become very difficult. Here, so what we now want to do is we want to include R1 and R2 also in the circuit. So this is how the circuit will get modified: R1 parallel R2, right? And of course this RS will be there, and this intervening capacitor Ci, this will act like a short circuit, so that we need not include here. So now Vi is going to be this voltage. So this is going to be the modified circuit, for which you will have to once again find out the transfer function. That means Vo by Vi. And now you can see that analysis is going to be a lot more difficult, because the CGS is now in parallel with the bias resistor. So nevertheless, at least in principle, one can carry out this analysis and then try to find out what will be the value for and what is the value that we are looking for here. Value for the very small frequency. So what we are trying to find out here is AVH for omega very small tending to 0, right? So actually when we are trying to find out this value, because this straight line is tangent to the actual curve at omega is equal to 0 or very small omega. So since this is a tangent for very small omega, so we need to actually analyze the circuit for very small frequency. So now you see that if we go back to the high frequency model for the complete circuit, here, this is the high frequency model for the complete circuit, but we are trying to find out what will be the voltage gain for low frequency. So once you go for the low frequency, what you will have to do is you have to neglect these capacitors because their impedances are going to be very high, right? So only for the purpose of finding out AVH for omega is equal to 0, you can take this circuit, and for this circuit try to find out VO by VI, and that is going to be the value that we were trying to find out, the magnitude of AVH for very low frequency. So now here analysis is going to be easier. Now you can see that output. So we can redraw that circuit below here. So for very low frequency, scenario is going to be like this. This is RD, this is VO, this is GM VGS. VGS is this voltage across R1 parallel R2 and RS and VI. So you can say that if we are considering the low frequency, why we are not including this CI? Because this low frequency has been obtained uh, a limiting case of the high frequency model, right? So that is why here CI will not be there. Otherwise, you will get the wrong result for this value that we are looking for, this horizontal one. Right. So that is why we are not including CI. Now you can see that it is easy to find out VO, which is minus RD GM VGS, which is minus RD GM VG, and VG is equal to voltage across parallel resistor R1 and R2. So this is RD GM, and voltage across parallel resistor R1 and R2 is going to be R1 parallel R2 divided by R1 parallel R2 plus RS into VI, right? So now from here you can find out VO by VI, which will be minus RD GM R1 parallel R2 divided by R1 parallel R2 plus RS. So here we see that we get the exactly same factor, same value that we got for the high frequency region value for the low frequency response, right? So now you can see that this GMRD is actually this factor which we have already found out for the low frequency response. So now you can combine these two curves and obtain this equivalent one, and here this value, now we know this value is going to be GM RD R1 parallel R2 divided by R1 parallel R2 plus RS, right? So this is the complete response of CS amplifier, magnitude response, and here we will have this omega P, and here we have omega P1, and when you carry out the experiment, actual response that you will get will be something like this. Yeah. Again, the maximum deviation will occur at these corner frequencies, and they will be very accurate at these tangent location points. So at these points. So in general, this is going to be the behavior of CS amplifier. And so for high frequency, we saw that why gain should decrease. Similarly, one can ask that for low frequency also, why the gain should decrease this region, why it should not be flat. So for that also, we can go to the equivalent circuit and try to see that why for even for low frequency, there should be low gain. So low gain means output should be low. That means this current should be low. So now let us see that what happens at the low frequency. So the impedance offered by this Ci is 1 by j omega Ci. So now what happens when you decrease this frequency omega, what will happen is this impedance is going to increase. So when this impedance increases, most of this input voltage that we are applying here will start getting developed across the CAI. So this CI will consume most of the input voltage. That means the voltage across this parallel resistor, which is VG, is going to decrease. Right. So if VG decreases, this current is going to decrease, and if this current decreases, the magnitude of the voltage developed across VO is also going to decrease. That means VO by VI is going to decrease. So we find that if you have taken any CI and if you try to reduce the frequency, input frequency, your voltage gain is again going to decrease, right? So it is only in the what is called mid band. So this frequency band will be called as mid band. Frequencies which are neither too low nor too high. Only in this band it will offer the maximum gain, and that is why this gain value that we have obtained is also called mid band gain. And so if you want to use this amplifier in real life, you should restrict your frequency of operation typically from omega p to omega p1, right? Okay, so now this is about the common source amplifier. In fact, most of the amplifiers, they will have this kind of behavior: low gain for low frequency, low gain again for high frequencies. And here we know that this portion results because of the external coupling capacitors. So here we have to include this Ci, so that this Ci was included here, so that the DC and the input time varying, they can be isolated, right? So here this capacitor Ci. So if you want to have a high gain even for low frequency, then you will have to find out how to avoid this Ci. In fact, this is what is done in differential amplifier. So we just wanted to isolate this DC from input, so we had to insert this capacitor. Similarly, in general, there will be one capacitor on the output side also. So actually output will be taken like this. And since we are considering the open circuit response, that means this RL connected here is infinite, and that is why this capacitor CO did not have any influence. We need not include in the circuit. Otherwise, if you include RL, then CO also has to be included, and this will again have adverse effect at the low frequency. Right. So all the external capacitors, they will affect the low frequency response of the amplifier. This region, sorry, this portion. Now we can see what will be the frequency response of common gate amplifier. So as you saw, the exact frequency response will be decided by the circuit you are considering. That means how many resistors and capacitors are there. But nevertheless, even the core of the amplifier has a response which is qualitatively similar to that of the exact one. Uh, so what we will do, we will, just to keep the thing simple, we will take the simple common gate amplifier, only the core. That means biasing part will be excluded. So here output will be from drain as usual, and the gate will be at certain DC, and then we will connect our input in this way, right? So when we connect this input in this way, we will have to provide a path for bias current. Bias current means DC current ID that flows because of VG. Because here we have a capacitor, and typically we have been showing our common gate in this configuration in this way. Here, like this. This is the simplest common gate circuit. But now you can see that in this case, your input source will continue to get DC current as well. So suppose we do not want this DC current to flow through this input, time varying input supply, then we will have to provide one path for DC and a separate path for AC. So that is how this will be done here, what we have shown here. So this capacitor we have put here so that DC does not flow towards VI, but once you have blocked the path for DC, there has to be some path from here to ground for the DC. So we do that by putting one current source here, right? So this is the circuit we are going to consider. This one is sufficiently general also. Right. So we have to then analyze this circuit for low frequency and for high frequency. So first, let us see the high frequency response. So for that, we will have to draw the high frequency model of the MOS. And in this case, we will have to short circuit all external capacitors, because frequency is already high and CI is also high. So that means this impedance is going to be very small. So that means this CI will basically act like a short circuit. There will be very little impedance offered by that. So here, when we draw the small signal model, high frequency signal model, this is CGD, CGS. Then we have here RD. And this is GM, VGS. Now there will be one capacitor from drain to bulk. Bulk, let us say that bulk is grounded. Bulk is grounded. So between drain and ground, and here gate is anyway grounded. So that capacitor will also actually appear in parallel with CGD. So this is DB, right? So here we have similarly, now the source is not grounded, source is rather connected to Vi. So there will be one capacitor between source and bulk which is grounded. So we see that gate is grounded, so that capacitor will actually appear in parallel with CGS. So this is CSB. So fortunately, in this case, we find that all the four capacitors, they get simplified to only two capacitors, one between gate and source, other between gate and drain. Right. So we can now analyze this circuit, and here you can write KCL at drain, right? So that will give minus VO by RD equal to sum of this current and the combined current through these two capacitors. So this becomes GM VGS, out of which VG is grounded. So this becomes minus VS plus this current going through both the capacitors can be written in terms of VO divided by parallel combination of both the capacitors. So I can write directly its value as CGD CDB in terms of S parameter. So here S is J omega. Right. So we have unknown Vs. So similarly, we can write KCL at source. So that will give rise to Vi minus Vs divided by Rs. This current, and then we have these two currents. So this current and this current, they will be equal to current through the both the capacitors. So plus Gm minus Vs is equal to Vs divided by 1 by S C GS plus CSB here. So now one can eliminate VS from 1 and 2, and then one can find out VO by VI. And if you write this thing in standard form, so this will turn out to be GM RD divided by GM RS plus 1 divided by S into RS CGS plus CSB divided by GMRS plus 1. So this is going to be one first order factor in denominator. There will be one more factor in the denominator, and that is going to be S RD C GD plus CDB divided, oh, that's it. So in this case, it is going to be only this much plus 1. So denominator has two factors, this one and this one. Both are fortunately a first order by default. So here what we have is a constant term equal to GMRD divided by RS C GS plus C SB, and two poles omega P1 is given by this factor. Sorry, here there will be one plus term also, plus 1 into. So omega P1 given by this factor, in fact reverse of this one. So that will be GM RS plus 1 divided by RS into CGS plus CSB, and omega P2 is equal to 1 by RD into C GD plus CDB here. So we have one constant term and two poles for the high frequency voltage gain of the common gate amplifier. So for this case, we can straightway draw the Bode plot, AV high frequency for common gate case. So there will be, let us say omega P1 is smaller than omega P2. So we will have horizontal response given by 20 log K and then minus 20 dB decaying line and then minus 40 dB decaying line. So we again see that voltage gain decreases with the increase in the frequency. And one can easily understand that that also again happens because this path, which is responsible for developing gate to source voltage, starts offering less and less impedance as omega goes up. So when omega goes up, impedance is less. That means VGS is going to be smaller. That means output voltage is going to be smaller. So same reason is valid here also. Why voltage gain should decrease with the frequency. Right. And this value here so here we have 20 log K. No, I made a mistake. This K is not this one. K is actually this factor. So it is GMRD divided by GMRS plus 1. This is the K. So this value is equal to K, and you can see that this K value is also equal to the AV when omega or S goes to 0. That means in this transfer function AV H for CG, when you take omega 0 or S0, then what you get is actually equal to this K, and this K is the voltage gain. This will, we will see, will become the midband gain. So now this is about the high frequency. Similarly, one can find out the low frequency common gate response or gain. So now this time what we will have to do, open circuit or exclude. So all the MOS capacitors, they should be open circuited and include all external capacitors. Right, so there is only one external capacitor, which is Ci. So that now should be included. And in this case, now if you draw the model, this is going to be the model. Ci is going to be short circuited here. Right. So this is the circuit in which we have to find out VO by VI. So at drain, we have VO is equal to minus GM VGS RD. And at source, one can apply KCL, we have only these two currents. So at source, we have Vi minus Vs by Rs is equal to Gm VGS. So here Vg is 0, so one can eliminate Vs from 3 and 4. One will obtain the voltage gain as Vo by Vi, and this is going to be voltage gain for low frequency. AVL is equal to Gm Rd CIS divided by S CI Gm Rs plus 1 plus Gm. So if you write this thing in standard form, what we will get is RDCIS divided by S into CI Rs plus 1 by Gm plus 1. So here we see that we have K is equal to RDCI. We have 1 0 at origin, and we have one pole. Omega P is equal to 1 by CI Rs plus 1 by Gm. Right. So in this case, when we do the Bode plot, AV at low frequency for common gate amplifier, then we, in the beginning, low frequency response will be decided by this 0. So the frequency response is going to be like this. So it will pass through this K, 20 log K, and then it will become flat after omega P. What will be this value? This value is basically AVL for omega infinity or S infinity. Right. So one can put S infinity in this equation to find out what will be the response. So for that we divide by S and then take the limit. So when you take the limit, this is what you will get, this factor, which is, so AVL for S or omega infinity is going to be RD divided by Rs plus 1 by Gm. Right, so this becomes RD Gm divided by Rs Gm plus 1. Now you recall that we got the same value for AVH when we take S is equal to 0 or omega is equal to 0. So both these values, they are exactly same, right? So that allows us to combine these two graphs, low frequency and high frequency plots, to get the complete CG response, frequency response, or the voltage gain plot. And this will turn out to be like this. So this is minus 20, minus 40, this is plus 20, and here we have omega pole for the low frequency response, and here we have omega P1 from the high frequency response, and this is AV CG magnitude, and this value, mid-band gain, this mid-band gain we saw will be equal to RD Gm divided by Rs Gn plus 1. Right. So this response is also similar to the common source. That means low gain for low frequency, flat gain for certain midband, and then again decaying gain for high frequency. In general, this is what happens. Only for differential amplifier, here we have flat gain for low frequency because we avoid the coupling capacitors.